Hello, good morning. Myself, Dr. Shaila Dinkarapte. Today, we will see the properties of Fourier series of continuous time signals. These continuous time signals will have to be periodic so that we can write the Fourier series for the signal. Let us see different properties of Fourier series. The first property is called as linearity property. Now we are using the linear time invariant systems unless otherwise stated. So once we know that our systems are LTI systems, it will definitely obey linearity property. Linearity property means if we have two signals and if they are scaled and linearly combined, then the Fourier series will also be scaled by the same factor and it will be added up or it will be combined, whether it is addition or subtraction. Physical significance of linearity. So suppose we have two different templates, two different signals. One signal can be decomposed as a linear combination of component signals, namely the sinusoids. Now Fourier series representation can be found for each of the signal and then we can add up the Fourier series to get the Fourier series for the linear combination. So this is linearity. We already know what is the meaning of linearity. We now consider time shifting property. So if the signal xt is shifted by time t0 towards right. So if we have x of t minus t0, how the Fourier series will be written down? The Fourier series coefficients will have to be multiplied by e raised to minus j n omega t0. So there will be some constant phase introduced in the corresponding Fourier series coefficients. Now what is the physical significance of time shifting property? Here we have suppose two templates, one template and the other template. Both are same signals. Only thing is one is time shifted with respect to the other. Then in that case, if we just compare the magnitude response of the Fourier series, it will remain the same. Only there will be a change in the phase shift by the angle theta, where theta is given by n omega t0 and t0 is supposed to be the amount of shift, whether it is shifted towards right or left. Accordingly, the sign of this shift will change. So this particular fact can be used for template matching because the magnitude response will be same, only there will be just change in the phase. So if it happens, then we can say that the two signals are the same, only there is some time shift. For example, if we have xt is equal to sine of pi t by 3, then how we can write xt as it is summation x of k e raised to j k pi by 3t. And what is xk? These are the Fourier series coefficients. So it will be equal to 1 upon 2j, because this is sine function. Sine can be written as e raised to j theta plus minus e raised to minus j theta divided by 2j. So that 1 upon 2j will come in picture over here. So this is the corresponding coefficient value for k is equal to 1 and same value but with negative sign for k equal to minus 1. And what will be the angle theta here? The angle theta will be 0 because there is no phase change in this sine of pi t by 3. There is no phase change added. Now consider this signal sine of pi t minus 2 by 3. So here it is time shifted by 2 samples. So again we will be using the same formula. In place of this t, we will write uh, the time shift t minus t0. In this case, t0 is equal to 2. So we'll have to write the coefficients for the Fourier series as 1 upon 2j minus 1 upon 2j, that is the magnitude as we discussed earlier. But there will be a phase shift also, e raised to minus j 2 pi by 3. It will be by 2 pi by 3. This is the phase change. So this is e raised to minus this for k equal to 1 and e raised to j 2 pi by 3 for k equal to minus 1. So for k equal to minus 1, it is 2 pi by 3 and here it is minus 2 pi by 3. So that is the phase change that will occur. Time reversal property. If corresponding signal xt is reverted in time, so if we have x of minus t, then what will be the change in the Fourier series coefficients? Fourier series coefficients will have the value as C of minus n. So wherever there is n, we'll have to replace it by minus n. So Fourier series coefficients for the time reverse signal are C of minus n. This means that Fourier series coefficients will have same magnitude, but the phase change is negative as that of the phase change for Fourier series coefficients of the original signal. The Fourier series coefficients of time reverse signal will be a complex conjugate of the Fourier series coefficients of the original signal because there is minus n. So if we consider this particular signal xt, we know that this is the corresponding Fourier series. Now, if we write instead of t, we write minus t, then what will happen? What should happen? The corresponding Fourier series coefficient values will remain the same. Only then thing this theta, here it will be plus and here it will be the phase will change, it will become minus, and here the corresponding phase will become plus. So the phase change will be taking place. Time scaling property. Now, if the signal is time scaled by the factor of alpha, if instead of writing xt we write x of alpha t, then what will be Cn? Cn will change to C of n, where omega will be replaced by alpha into omega. So what is the physical significance? Fourier series coefficients of the time scale signal with scaling factor of alpha will have same magnitude response. Only thing is omega will be scaled by the factor of alpha omega. So see here, if it is, see this t is scaled by a factor of 2. So instead of writing pi t by 3, I am writing 2 pi t by 3. So 2 pi t by 3 will be the corresponding omega, and the corresponding xk will remain the same. Only this omega will change to alpha omega. Find Fourier series of a time scale signal by a factor of 2. So I think we considered one signal x of t as sine 2 pi t earlier in the previous presentation, previous video. Now in that case this was 1 and this was 1. Now we are considering the signal which is scaled by the factor of alpha t. Alpha is equal to 1 by 2. So in this case we are considering that in this case W will be replaced by W by, not W, it is omega. Omega will be replaced by omega by 2, and the corresponding xk will remain the same here. So what will happen? X of t will be written as 2 by pi plus this particular 2 by 1 upon 4k square into pi. This will remain as it is. Only thing is instead of e raised to 2 pi kt, I will have e raised to j pi kt. It is scaled by a factor of 2, no? So this 2 over here will go away. Consider the property of differentiation in time domain. If the corresponding signal is differentiated in time domain, that means if we have one signal, if we have another signal and we find that another signal is a differentiated version of the first signal, then how to find out the Fourier series coefficients? We just have to multiply the Fourier series coefficients by j n into omega. When the signal is differentiated in time domain, its Fourier series coefficients plane rotates by an angle of n omega. So if you consider Fourier series coefficients, then the entire plane will rotate by the angle of n into omega. In the integration property, if you integrate the signal, then what will happen to the Fourier series? Fourier series coefficients will change to the original Fourier series coefficients divided by j n omega. Now in this case, it will also be rotating the plane. In this case, the signal is, when signal is integrated in time domain, its Fourier series coefficients plane rotates, but it rotates by the negative angle 1 upon n omega, minus of 1 upon n omega. It rotates on the in the clockwise direction. You see, it will be rotating in the clockwise direction by minus angle, and in the earlier case when it is differentiated, it will rotate in the anti-clockwise direction, that is the positive angle. Consider the convolution property now. If one signal is transformed to Cn and another signal is transformed to Dn. And if we convolve the two signals in time domain, how the convolution will result in the transform domain? In the transform domain, it will be the multiplication. So if we have the convolution in time domain, we'll have multiplication in the transform domain. And if we have multiplication in the time domain, we'll have convolution in the transform domain. This fact I think we know already. So physical significance of convolution property. When the two signals are convolved in time domain, the Fourier series coefficients get multiplied. Now because the convolution is the costly affair, Fourier series coefficients can be found and they can be just multiplied. So when you multiply it sample by sample, you will directly get the Fourier series coefficients of the convolved signal and then you take inverse Fourier series. When the signal passes via the LTI system, when we consider the generation of the speech signal, the excitation is generated at the larynx and then it passes via the vocal tract. So, how the speech signal is generated? Speech signal is generated as a result of convolution of the excitation with the impulse response of the vocal tract. So, how to find the corresponding Fourier series representation for the convolved output? We may just find Fourier series of the input signal and the impulse response of the LTI system and then multiply the two Fourier series. Modulation property. Now, on the other hand, if we have the two signals multiplied in time domain, then what will be the transform? The transform will be in the convolved state. So where this will be used? This will be used. This is why this is called as modulation property, because this will be used in the modulation. So in the modulation, we have the carrier signal and it multiplies with the message signal and then we get double sideband suppressed carrier modulated signal. Now the Fourier series of the modulated signal is a convolution of Fourier series of component signals. So we can find out the Fourier series of the modulated signal by just taking the convolution of the Fourier series of the two independent signals. Conjugate symmetry property. If x of t transforms to Cn for complex valued xt, of course we are considering x star t is supposed to be the complex conjugate of x, then the corresponding Fourier series will be C star minus n. C of minus n is equal to Cn star, that is for real it will not be considering it as star because it will be same as the star. Complex conjugate will be the same in that case. Now physical significance of conjugate property. If the signal is real, Fourier series coefficients for signal show the conjugate property. If the positive Fourier series coefficients are complex conjugates of the negative Fourier series coefficient. So this complex conjugate property we already know. There is something called a deep Parseval's relation. So if x1t transforms to Cn and x2t transforms to Dn for the complex valued xt, then 1 upon t integration t to t plus t, where t is the capital T is the period, x1t into x star of t, which is the complex conjugate of x2 dt, is equal to summation n varying from minus infinity to infinity Cn into Dn star. So what this basically indicates is the energy in time domain will be same as the energy in the transform domain. There is no energy loss at all. So de Parseval's identity says that the energy of the signal in time domain is same as the energy of the Fourier series coefficients. When the signal is transformed in the frequency domain, its energy does not change. Its energy, you can say, it is preserved. Whatever is the energy in the time domain, it is preserved in the transform domain as well. Now let us see how we can recover the continuous time signal from the Fourier. So suppose we have the Fourier series. This is the Fourier series given to you. Cn is equal to j into delta n minus 1 minus j delta n plus 1 plus delta n minus 2 plus 2 into delta n plus 2. So whenever there is n minus 1 coefficient, you will also have n plus 1 coefficient because it is symmetrical, isn't it? That we know. And if you have the coefficient at n equal to 2, you will also have the coefficient at n minus 2 and it will have the same value. right? So this is how the Fourier series would look like. Now, how you can recover xt? You can recover xt as equal to, xt will be equal to summation over n cn e raised to j n omega t. What is j n omega t? J omega is 2 pi ft, so j n pi t. I can write xt as j. So this is that j e raised to j pi t, because there is only one sample, shift of one sample, so j pi t. Now for this signal we'll write it as minus j into e raised to minus j pi t. For this we will write e raised to j2 pi t. For this we will write e raised to minus j2 pi t, because this is existing at n equal to minus 2. So this will be basically n pi into t. So here it is n is equal to minus 2. So n will be equal to minus 2. So e raised to minus j2 pi t. Here n equal to 2. So it is e raised to j2 pi t. Here n equal to minus 1. So minus j pi t. Here n equal to 1. So it is j pi t. Now if you combine these two, e raised to j pi t minus e raised to minus j pi t, it will be 2j sin pi t, and j into j multiplied, it will become minus, plus this will be equal to 2j multiplied by 2, so it will be 4, not j. Here in this case j will not appear because it is a sine cos component rather than sine. So that 2 will appear, 2 will multiply by this 2, so it will become 4, and then cos of 2 pi t. So this is how you recover the signal. So remember that whenever you have delta n minus 1, you recover it as e raised to j pi t. If it is n minus 2, you recover it as e raised to j 2 pi t. So this is how very easily we can just recover the continuous time signal for the from the Fourier